In the lecture 16, we started dealing with the fluctuating load, and in that what we did, because of the fluctuating load, we get fluctuating stresses, and we showed that there can be several types of fluctuating stresses. For example, if you take it can be something like this. So this is your minimum. This difference is your amplitude, and sigma, that is sigma A, is equals to sigma max minus sigma min, and sigma mean is sigma max plus sigma min divided by 2. So your average stress would be somewhere here, whereas maximum and minimum will be there. And when these kind of fluctuating stresses, we have seen that the failure occurs even though the sigma max or sigma min, all these things are well below the elastic limit, or well below the kind of yield strength of the material, so, or the strength of the given material. So this is quite an important thing, because most of the components that we design in mechanical side are, we want it to endure for several cycles of several working cycles. So that means if it is, when we design it for a static load, we design it for the maximum load. But even though you are not subjecting it to the full, even if you are operating in well below the material strength, at a lower stresses over the time on repeated loading and unloading, it would fail at less than the intended life. So that means we need to deal with the fatigue strength separately, and we define the fatigue strength as it is the maximum reversed stress that a standard specimen can sustain for a given number of cycles without fatigue failure. So that manner, and we showed that fatigue strength can be obtained using fatigue testing using Wheeler diagram, or by testing it we develop something called as SN diagram. Typically it would look like a log-log or a semi-log axis. Here it shows a fatigue strength versus your number of cycles And we showed that it would have something of this shape. So this limit is something called as endurance limit. And this portion is a low cycle. This portion up to here is finite life, and beyond this it is infinite life. So this is a Sn diagram that can be obtained experimentally. So this is the different strength. That means if you're operating at very high stresses, that is when this is 10 to the power of 0, this can be 10 to the power of 1, and generally this would be around 10 power 3. This would be around generally 10 power 6 for steels, mild steels. So you see anything that is less than 10 power 3 is a low cycle fatigue, and anything about 10 power 6 is high cycle fatigue. So in that man, or beyond 10 power 3 and high, above values can be called as high cycle fatigue. So this is high cycle fatigue. So now we want to make use of this when we are designing in our design procedures. So for that, we need to understand endurance limit, and we also defined it last time. Our endurance limit is defined as the limit of a material where the complete reversal of maximum amplitude on the standard specimen can sustain for an unlimited number of cycles without fatigue failures, or in short form you can call it as is the limit above which it has life. So with this we have done in the previous class. Today what we'll talk about is how to incorporate. We know that if the defects are present in the system, then the fatigue, under the fatigue, it is more susceptible to failure, and hence we'll introduce something called as notch sensitivity factor. And using this, what we'll do is we'll try to design certain components which are subjected to fatigue loading or fluctuating loads. So the first one today we'll talk about is notch sensitivity. So it is defined as the susceptibility of a material to succumb to the damaging effects of stress raising notches in fatigue loading. It is defined as Q is equals to you can see that here these are the notches. So because of the presence of the notch, the stress contours are deflecting. So these notches, the limit of this notch can be a crack or a wedge or something like that. So these things all disrupt the things. So under these things, the stress risers will be there, and how the material behaves under the influence of notches is measured through this notch sensitivity factor Q, which is mentioned above. So next, endurance limit, which we thought is kind of infinite life, but that limit has been obtained thinking that there are no notches present. Okay, that is for the kind of Q is equals to kind of a zero kind of a material. Okay, but in actual endurance limit is to be lowered by the presence notches due to stress concentration. Further, these things it has been found experimentally that some materials are less sensitive to stress risers in fatigue loading. Now, actual reduction in the endurance limit of a material due to stress concentration is less than the amount calculated using theoretical stress concentration factor Kt. So, and hence we can actually define our Kf as endurance limit of notch-free specimen divided by endurance limit of notched specimen. So, and hence, as we have given notch sensitivity, which is defined as Q is equals to Kf minus 1 by Kt minus 1, or Kf can be obtained if we know our notch sensitivity factor and the theoretical stress concentration factor Kt. Kt is obtained through analytical methods, whereas Kf is the actual thing that is there. Okay, and so now if we have to correct the endurance limit, there are several things that has to be accounted, not just the Kf. So we will go and deal with how to correct the endurance limit. Okay, so let us rewrite again the corrected endurance limit. And it is not only because of notch sensitivity, there may be surface finish, there may be amount of the load, size of the specimen, temperature, and other things that are actually involved that would kind of change the actual endurance limit. So for design purposes, we need to account all these factors. So what we'll do is we will try to address these issues first so that we can use the corrected endurance limit when we are designing certain machine components at the end of the lecture. So we know that by taking into account the fatigue stress concentration, the corrected endurance limit for actual part can be SE dash by KF, where SE dash is the endurance limit of the standard rotating beam element. In general, for steels, SE dash is equals to 0.5 times SUT, and for cast steels, your SC dash is 0.4 times SUT. Now this is the SC kind of a value which can be obtained from the ultimate tensile stress. Then the next thing is, not only this, there are several other influence factors. So those are, in practice, there are several other factors that influence the actual endurance limit as given by SE is influenced by the surface finish, K-surf, by the size, by the type of load applied, by the temperature, and the reliability you require of the things, and the standard specimen size and notch sensitivity factor. So this is quite an important factors of the relationship, where K surf is surface finish factor, K size is size factor, K load is load modification factor, K temp temperature modification KREL is reliability factor. Now, how are these all factors are determined? That is one of the prime question. So these things, these factors are either calculated using empirical relations or taken from design data charts. For example, if you look at first one, surface finish factor. So K-surf is obtained by an empirical relationship where A SUT to the power of B, where A and B are some material coefficients and SUT is in terms of MPa, And for different surface finishes, further, if by computing in this manner ksurf happens to be greater than 1, then we need to reset it to ksurf can only go up to 1. It cannot increase it, it can only decrease it. So those things are so now if you look at it, let's say if the surface finish is well grounded, that whatever is the material SUT, you use a factor of 1.58 and an exponent of minus 0.085, and if it is machined or cold drawn, then you will use A as 4.51 and B as minus 0.265. As forced condition, you use A as 272 and B as minus 0.995, and these things was actually proposed by by Shigley and Mishke. Now, the second thing, we'll make use of this chart like previous class to kind of solve some problems. So we will make use of it. So note it down. So the next thing is the kind of size factor. Now, we know that greater the size, the higher the chances of failure. So in case of bending, and torsion, the case size is taken as d divided by 0.3 to the power of 7. This can be approximated as 0.879 d when d is measured in inches and it is between 0.11 to 2 inches. The same thing can be also written in mm, but I'll give it later. So if it is greater than 2 inches, for that we use for d greater than 2 inches to 10. And if you want to measure d in terms of mm, the same expression can be written as 1.24 t to the power of minus 0.107 if it is between 2.7 to d, or it is 1.51 d to the power of minus 0.157 if it is between 51 mm to that of 254 mm. And this is for bending and torsion and for the circular cross sections. But not necessarily all the rotating components are of circular in nature in most of the time. So is of circular in cross section. So then people see, it is in general what happens is the region which is highly stressed are the ones which are highly are susceptible to the failures, and because of the defects that are present in those regions. So Google has come up with an equality which most people use is they take whatever is the rotating non-circular cross section and take its 95 percentage of stress or more stressed area, and then they equate it to equivalent 95 percentage of circular cross section. This circular cross section can again be two types. One is rotating and or non-rotating. So generally we know that rotating components has higher 95 percentage of stressed area compared to non-rotating stress area. So for standard specimens, you can we will give for 4 standard specimen how to convert this using an empirical relationships as given here. So it's 0.0105 or 1046 d square, and hence the effective diameter for this non-rotating cross section would be 0.370 d, considering only 95 percentage of stress or above. Now, similarly, for a rectangular cross section, the equivalent circular cross section would be 0.808 square root hb, and for a I section along 1 direction, it is this value, and along 2 direction, if you are bending it, then it would be 0.05 VA. And if you are kind of similarly for a kind of a C section or a channel section, it would be axis 1 direction is 0.05 B and other direction is 2. This is the kind of case size when you are doing it for the torsion and the kind of torsion and bending loading. Okay, so for axial loading, if you have axial loading, we just take K size is equals to 1. So this is with respect to K size. The next one is the for the K size is equals to 1 when you have for the correction factors, and then the next size factor which we'll consider would be the reliability factors. K load is equals to 1 for bending, and it is equals to 0.8, and it is taken as 0.59 for torsional loading. Next is the temperature factor. Temperature factor greatly varies with the temperature, so it will be generally specified if it has to be considered into the picture. Otherwise, you can take by default K temp is equals to 1, and in the last factor is the reliability factor. See, reliability is like with if you want to avoid, let's say if we are having a we are operating something important, let's say a time machine or something like that, where we want number of power failures has to be very less, so you want 99.99999 percentage of time the power failure should not happen. Or let's say if I'm only using for a home appliance, not a kind of very research thing, I could live with 90% of the reliability time it would be available. So, but depending upon the things that you have, that will also dictate the amount of kind of safety factors or the factors I need to kind of consider when I'm designing the power plant, right? Because if you want more time, the uninterrupted power to be there, it has to, the downtime has to be very less, and it has to avoid many failures. So like that, we'll give it a kind of a tentative table which will take care of the reliability factor. You can see that if you want only 50% reliable, then you can just make your K reliability as 1. But if you want 99.9% of the failures are to be avoided, then your factor goes to 0.753. That means you are lowering the endurance limit, so the operating regimes becomes lower. And if you want to be reliable at 99.999 times, then further endurance limit has to go down drastically. You can see it with an exponential decrease. You can see sizable decrease in the K reliability index. So now we know all the corrected factors, and it's how they influence the endurance limit. Now what we'll do is, using these values, we will talk about designing a component. So the design of a component under fluctuating load can be of two types. Further, we are talking about the case of complete reversal of load. First thing is complete reversed stress. This is one thing. Plus, we are talking about design for this given scenario. In a complete reverse situation, what would happen is the amount of maximum has to be the amount of maximum, and minimum are of the same magnitude but of different things, so that the mean is equals to 0. So in this, that is sigma max plus sigma min divided by 2 is equals to 0 is a case of complete reversal. So sigma max is equals to minus of sigma min, and hence this will be there. Under this, we are talking about design. So design is of two types. One is, we know that we are talking about life, so it can have infinite life, like immortals, and mortals are like finite life, like us. So finite life. So if you want to design for infinite life, things are pretty easy, because we already discussed something called as endurance limit. And for a given surface finish and other things, we even corrected the endurance limit. So all we need to make sure that the maximum stress in those regions has to be less than the corrected endurance limit. So case 1, infinite life, corrected endurance limit is the failure. So your maximum or minimum stress magnitude has to be less than the corrected endurance limit. That is the only thing that you need to worry about. But not all components are designed for the finite life. Sometimes the infinite life. Sometimes the infinite life can be somewhere around 10 power. The endurance limit may be at some place, but sometimes we may be operating at higher stresses than the endurance limit. Then obviously that component, when it is operated at higher stresses, it will have finite life. So it has to be designed for a finite life. For example, if you nowadays, if you go ahead and buy a laptop, they will tell you that your battery guarantee is only or warranty is only for the 1 year. And you obviously see that in most of the cases, the battery fails somewhere in 13 months or 14 months. So if the company underpredicts it, for example, so more, so the replacing cost will be more on the company. Okay. Or let's say if it kind of over predicts it, so then what happens, it says that we will replace in 13-14 months, but let's say in every case the failure is happening in like 3 years from the day you purchased, then what happens is they are over designing it. So It will be actually, they could have actually, they are incurring, it's a over design. That's the reason it is having more life than it was been intended. Why I have given this cycle is every time you switch on, switch off a battery, it will be, there will be a charge cycle in there. And when you discharge or charge, uh, when you start, that will be one cycle, or when you charge or discharge, that is one kind of a cycle. So these are the cases of where a fatigue or a fluctuating loads are there. The fluctuating loads need not be mechanical in nature. It can be electrically driven. So in that case of an example of a laptop battery is an electrical in nature. So anyway, now let us understand how to design a component if it has to have a finite life. Okay, so now in the case of finite life, what we'll make use is we will have the uh, SN diagram, and using SN diagram, we will try to solve the or show the design procedure. So let us say that we want to design uh, this component for, let's say, n cycles. Okay, let this n be something like log is. So I'm writing in terms of log scale just because my plot is in under. So for this number of cycle, I want to design it. Let's say if I want to design this thing for the thing, we know that maximum stress at which I can operate I need to find out the corresponding SF. So for that, what I do is, first let us see the corresponding SN diagram. Take this SN diagram and take your SUT, and you just multiply with 0.9. Even though it is 1, we just take some kind of safety factor and then just multiply and consider it as 0.9, and instead of 1 SUT, we'll just do it for a 0.9 SUT. And so, or you can even totally construct it from the full face, but we know that at the limit of boundary of the higher and lower limit, this would be around 0.9 SUT. So locate a point. First thing is locate a point, locate the point capital A with coordinates as 0.3, sorry, 3, this is 3, and 0.9 SUT. So this is this point which has been located. Next, locate the point with coordinates as 6, and this is a log plot, so I should have written it in the log scale. log 10 of endurance limit SE, and then join the line AB, and line AB is the criterion for finite life problems. Now, in order to get our actual strength, what we'll do is, so we have located A, B, drawn a line like this, and depending upon life desired, let's say in our case n is equals to 10 to the power 4.5. Okay, so draw a vertical line passing through log 10 of n. In this case, since it is here, log 10 of 10 to the power 4.5 is equals to 4.5. So at 4.5, draw a this vertical line intersects AB at F. Now, what I would say is join, or let's draw a horizontal line FE intersecting vertical axis at E. So if I draw a horizontal line, it would intersect, this is the vertical axis, at E. So E corresponds to fatigue strength to n cycles. So this is there in terms of log 10 SF. So E is log 10 SF. You want to take the SF, you kind of raise it to the 10 to the power of something of what you have got, that will give you the SF value. So in this manner, you get for different things, you interpolate it in this log cycle in this given manner, and the interpolation is done between A and B, where A is with coordinates 3 and 0.9 SUT, and B is 6 and log 10 of SE. So this is the standard procedure for to kind of design a problem with finite number of cycles. So with this, what we'll do is today we'll solve a couple of problems before we leave, and so that we can understand how the design can be carried out. Let us do one example for a infinite life and one example for a finite life. So let us consider this problem. Consider a plate made up of steel of grade 20C8, which has an 440 Newton per mm square, and it is obtained using hot rolled and it is hot rolled as shown in figure below. Will give the figure, and it is subjected to a completely reversed axial load of 30 kilonewton, and the notch sensitivity factor Q can be taken as 0.8, and the expected reliability is 90%. The size factor is 0.85. The factor of safety is 2, and we need to determine the plate thickness for infinite life. Now, so this is the problem at hand. The total load is varying between from plus 30 kilonewtons to minus 30 kilonewtons. The width of the plate is 50 and the diameter is given as 10. And what we need to do is we need to obtain the thickness of the plate that can carry this load without having a fatigue failure. So we know that the P max is equals to 30 kilonewton, P minimum is equals to minus 30 kilonewton, and SUT is 440 Newton per mm square. Factor of safety is 2. Reliability is equals to 90%. North sensitive factor is 0.8, and K size is equals to 0.85. So now what we'll do is we'll try to obtain the endurance limit. Endurance limit in this case, because this is made up of steel, for steel we said that SC dash earlier is 0.5 times SUT, so this is 0.5 times 440, that is equals to 220 Newton per mm square is for the standard specimen. Okay, now since it is hot rolled, surface finish is hot rolled. If we go back under hot rolled, we need to put A as 57.7 and B as 0.718. So it comes down to be equals to 0.67. Similarly, size factor, K size, it is 0.85, which is given. Then reliability factor, K reliability is, if you look at the reliability table, for a 90% reliability, the value is 0.897. And load factor, since it is axial loading, K load is equals to 1. Temperature factor, since no temperature has been mentioned, K temp it can also be taken as 1. Now since there is plate with the hole, we have stress concentration factor. We know that when you have a plate with the hole, we have W by D, we take D by W ratio, and so for D by W in our case is 10 by 50, that is equals to 0.2. For 0.2, for a 0.2, we see the value of KT, theoretical stress concentration factor, is around 2.51. from the table. And our north theoretical stress concentration factor. And Q, north sensitivity factor, Q is given as 0.8. So we can obtain our actual Kf is 1 plus Q into Kt minus 1, that is equals to 1 plus 0.8, 2.51 minus 1, which will come as 2.208 as our actual. Now corrected endurance limit is given as K surf, K size, K load, K temp, K reliability, SE dash divided by Kf. So we can write our SE is equals to 0.67 is the surface size is 0.85, load is 1, temperature is 1, reliability is 0.897 into 220 divided by 2.208. If you kind of calculate it, this will give you 50.9 Newton per mm square. So this is the kind of endurance limit, that corrected endurance limit, which is there. So which we call it as allowable limit. So we know that sigma A is equals to SC divided by factor of safety. So 50.9 divided by factor of safety 2 happens to be 20. Is for axial load. Okay, so happens to be, let me just quickly calculate this. For the axial load K load is taken as 0.8. So we have to, for 0.8 times SC will be there. So in this case, it gives you as 20.36 Newton per mm square. And further, now if you calculate the actual stress, now we know sigma A is equals to P divided by W minus D into T, which is, we know it is 30 kilonewtons or 30 into 10 power 3 divided by 50 minus 10 into T, and we know sigma A is obtained that. On simplification, we get T is equals to 36.84 mm. Make sure we obtain the thickness such that it can take a reversal of load, complete reversal of load from 30 kilonewtons to minus 30 kilonewtons under the fluctuating load. So this is the case for the finite infinite life. Now, if the second example we'll deal today is finite life problem. For that, we'll consider a forged steel bar of 50 mm in dia, subjected to a reversed bending stress of 250 Newton per mm square. The bar is steel of grade 40C8. That means SUT is equals to 600 Newton per mm square. We need to calculate the life of the bar for a reliability of 90%. So we know that in this case our SF is sigma B, which is 250 Newton per mm square, and our SUT, SF is the operating fatigue stress, and SUT is the ultimate tensile thing, which is of 600 Newton per mm square. Reliability is 0.9, and SC dash, since it is steel, which is would be 0.5. SUT, that is, comes out to be 300 Newton per mm. As forced bar, the surface value turns out to be, if I approximate it, this comes out to be 0.44. Next one is the size for the 50 mm dia bar. K size is obtained using the expression which we have given earlier. K size, we need to take it as 1.24 d to the power of minus 0.107. So if you apply 1.24 50 to the power of minus 0.107, it happens to be a value of close to 0.85 as your size. And for 90% reliability, K reliability is same as last time, which is 0.897. Looking from the table from this place, 0.90%. And now our SE is equals to K size, surface K size, K reliability times SE dash, which would be 0.44 times 0.85 times 0.897 times 300, which comes out to be around 100.64 Newton per mm square is our endurance limit. Now, once this is there, then we will draw the SN curve to find locus of finite life. That is, we need to draw the AB line. So for that, what we do is we construct this one in a log 10 SF, and this one is log 10 of n. For a value of 3, we need to locate log 10 of 0.9 SUT, log 10 of 0.9 SUT. If you calculate in our case, it is log 10 of 0.9 into 600, which is log 10 of 540, which is 2.7324. So this point, which we'll call it as point A, and point B is located at 6 and log 10 SE, which is log 10 100.64, that happens to be 2.0028. So let's say this point is 2.0028. This is point B. We'll draw a line between A and B, and we know we want to design this. We are operating this one at 250 thing, so we know our SF is equals to 250 Newton per mm square. So log 10 SF is equals to log 10 250, that is equals to 2.3979. So what we do is we locate this point of 2.3979, draw a horizontal line, and then obtain this point F given this point E, and then we'll project it downstairs. So now we have obtained a SN curve. So in order to obtain our EF bar, we need to obtain dB bar cross AE bar by AD bar by similar triangles, that you can see that this is 6 minus 3 is the dB bar, and AE bar is 2.7324 minus 2.3979 divided by AD bar is 2.7324 minus 2.0028. If we try to solve that, this is equals to 1.3754. But what is EF bar? Our EF bar is same as log 10n. So by equating it to log 10n, log 10n is equals to 1.3754, then n is equal to 3736.2 cycles. So the life of this component when it is operated at 250 Newton per mm square is 23736 cycles is the life. With this, we will finish today's topic. Tomorrow we'll again meet at